Alright, so we started out on page 360, looking at kind of joining together what we have just done and what we are moving forward to do. Of course, last chapter we were looking at discrete probability distributions. Obviously, then the next logical thing to look at would be continuous probability distribution, which is where we are going to begin our discussions today. So, of course, we're talking about things that are measurable. We're talking about things that have fractions and decimals as possible answers. Either we can stop talking or I can start reading. Let's pay attention. So, the first question is asking about the binomial histogram that they have there on page 360. And you can see it up here. And it asks, of course, what the width of the bars was. Now, of course, we're talking about something that is discrete. We're looking at binomial distribution. And so we're talking about 0, a 1, a 2. And so the decimal fractions don't actually apply. So how wide is the bar? 1. Each one represents a single individual number in the possible sample space. Of course, then we know how a histogram works. We have our random variables on the x-axis. Of course, our y-axis represents the probability. So the height of each bar is representative of the probability of those numbers occurring for whatever this experiment happens to be. As people explored this more, they realized that there's actually a bigger connection that we can look at, and that flows into the concept of area. If you look at this rectangle, of course, it has a width of 1. This one has a height of about 0.3. There's 0.3. And so what is the area of that rectangle? 0.3, 0.32, whatever it happens to be. Because, of course, when we're finding area of a rectangle, we're taking width times height. So if the width is 1, height is indicative of whatever the probability is. That means when I take 1 times the height, which is the probability, the area itself is also going to be equal to the probability. And so they found that to be very interesting and realized that they could then transfer that information into continuous variables as well. Obviously, in continuous situations, we can look at the probabilities of various decimals and fractions and amongst our 1, 2, 3, 4, 5, but those probabilities can be found using area. So a lot of what we're going to talk about today are area calculations. So the chapter actually began with a little example scenario that they gave us about a friend that we have that's always late. Up to 30 minutes, in fact. I don't know if you have any friends that fall into that category, or maybe you are that friend that happens to always be late. But that, of course, can be, a little bit of a pain in the butt. You tell them you want to meet at 10, they show up at 10:25. You've now wasted 25 minutes waiting for them, which can be annoying. So, they mentioned, of course, that the person could be up to 30 minutes late. It's equally likely that they're anywhere from 0 to 30 minutes late. And so because they mentioned that it is equally likely, that is why we can use a uniform distribution to actually describe this situation. So we have any possible value between 0 and 30, and it's all equally likely. So we end up with a graph that looks something like that. They could be anywhere from 0 to 30 minutes late. Everything has the same chance of happening, so it's just a very straightforward, very boring sort of graph. What type of shape does that graph make? Yes, uniform, but in geometry, what type of shape does that graph make? A rectangle. So we have a beautiful rectangle for which we can then, of course, determine some areas, which is very helpful. Now, keep in mind that because we are talking about time, which is continuous, there are a gazillion possibilities. Yes, our friend could be 12 minutes late. They could be 12.2 minutes late. They could be 12.25 minutes late. They could be 12.2518 minutes late. There's a whole bunch of options there when you're allowing decimals and fractions in your calculation. And so really you have an infinite number of possibilities. So to deal with that, it turns out that for a continuous random variable, you cannot calculate a probability for exactly one item. So we are never going to find the probability that they are exactly 12 minutes late. It's not going to happen. Because, let's think about that. Let's talk about exactly 12. That would be right here on the graph. You should make straight line, but it didn't make straight line. What is the area of a line? The width, what is the width? A line doesn't have width. A line is one-dimensional. It's only tall, in this case. So you can't calculate an area of a line. It's only one-dimensional. And so for that reason, we will not calculate probabilities for exactly one number. Okay? If you ever see a probability with a probability of exactly 17, you can't find that probability. It does not exist because that line does not have any area. So we will only look at ranges of values. So if we want to calculate for 12, we might figure out the probability that they were between 11 and 12 minutes late, or between 12 and 13, or between 11 and 13, say between 12 and 12 and a half. But we have to have some sort of range in order to calculate these probabilities for continuous random variables. Now, of course, we have two properties that must be true. These go back to the same probability rules that we've had since chapter 5. The first one, of course, is that the total area must equal 1. Because if your area of your graph is representative of your probability, of course, the total probability must equal 1. Therefore, the total area must equal 1. Also, of course, you can't have anything that's negative. You can't have anything that's over 1. So the height of the graph must be greater than or equal to 0 for any possible value. So you can't have, dip it into the negative area because you can't have negative probabilities. So as I've kind of indicated, we're going to look at the area under the curve. For uniform distributions, that's pretty easy because they're all rectangles. So we're going to look at the range of values over which we're trying to calculate a probability. We'll calculate the area for that particular rectangle, and then we will know the probability of our event. Now you may have noticed, of course, that up at the top is this probability density function. You might remember that in binomial and Poisson, we have the binomial PDF and the Poisson PDF, and that PDF stood for probability distribution function. When you head over to continuous, they keep the PDF acronym, but they change it to mean probability density function. And that's again because we're talking about area. And so density is a measure of how much stuff is being covered in a certain amount of area. And so that is why it's referred to as a density function rather than a distribution function. Any questions on those, which are 1 through 7 from the homework? All right, so we go to number 8, which says, what is the probability that your friend is between 10 and 15 minutes late? So we're actually going to go through the process of how one would calculate the probability using that uniform graph that we established a few moments ago. So you may want to maybe have the answer already done. Maybe you have it on the back of your paper. Maybe you want to write it on your separate sheet of paper. That is up to you. So we have our graph here. Our friend could be between 0 and 30 minutes. We want to know the probability that they are between 10 and 15 minutes. Now, because, of course, we're dealing with continuous, you might remember as we were discussing continuous things last time, we can use inequalities. So we can use inequalities to represent these situations as opposed to 0, 1, 2, 3, dot, 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 and all that stuff that we did for discrete. And normally in situations of between, people use the less than signs and we use the numbers on either side with their x in the middle. So we want to calculate the probability that our friend is between 10 and 15 minutes late. So I have this beautiful graph that represents their probability situation. And so I'm going to figure out where 10 to 15 minutes is. Any other question? Okay. That is not part of our scenario. Certainly, in practical sense, yes, that could happen, but again, not part of our scenario. So we are between 10 and 15 minutes late. So that represents this chunk of space, that chunk of area underneath our curve. And that area, when we calculate it, will give us the probability that they are between 10 and 15 minutes late. What is the formula we said we'd use earlier for the area of a rectangle? So we have width times height. So what is the width of a rectangle from 10 to 15? Well, it does not actually matter whether it's inclusive of 10 or 15 because you cannot calculate the probability of exactly 10. However, you can, of course, calculate the probability of 10.001, 10.002. And so that's why it actually doesn't matter whether you have a less than or less than or equal to. Anything up to 10 works, and 10 itself doesn't have a probability. All right, so we have our width. What is our height? Let's write our graph. Is there anything there? No. We need to figure out that height. Okay. That height, of course, is something that we need in order to calculate this answer. So how do we figure out this height? Well, let's figure out what we know. Again, this is all based on area, and we have a rectangle shape for this whole graph. So we can use that same area equals width times height to figure this out. We need to figure out the height, so that is what we are missing. What is the width of our graph? We want the whole graph now. The width of our graph. What is the total area of our graph? I think someone may have said it for yourself. We do know. It's 1. So the area under the curve is 1. It's always 1. Because everything has to add up to 1. Because it's 1. 1. 1, 1, 1. Very similar to mine. 1. So we know the area is 1. What do we need to do to find height? Divide by 1 back. So what is our height? Oh, sure. 30 because my graph is 30 wide. Because the area of which I'm calculating probability is only 5. This we are looking over the whole graph. Right. We need the height for this little probability. Okay. Other questions before I move on? Alright, so we have our width for our probability. What is our height? 30. You might remember from practice multiplication days that really this is 5 over 1 times 1 over 30. Multiply straight across. So what does that simplify to? 1 out of 6. So there's a 1 out of 6 chance that our friend is between 10 and 15 minutes late. Which is roughly 17%. 30 is the width of the total graph. 0 to 30. Right. The total area in that rectangle can only be 1. Sure?
using that, can you be able to find out what time you would arrive?
No. Simply calculating the probabilities of when they will arrive.
Yeah, like you can't calculate how you
You can calculate the probability that they'll between 18 and 21 minutes. You can calculate the probability that between 0 and 9 minutes, but you can't actually figure out when they will come. Because it's equally likely, hence the uniform graph, they will come at any one of those times. Wait, can we stop talking?
If you use the same width, like for a different section, isn't it the exact same?
That is correct. So if we looked at the probability that they were between 25 and 30, we would still have a 1/6. Between 0 and 5, would still be a 1/6. Other questions? All right, let's try this one. Our stage situation. Let's look at the probability that our friend is 24 or more minutes late. So we want the probability that they are 24 or more. So once again, we'll do our width times the height. 24, of course, is here. Of course, we will end at 30 because we know that they were going to be up to 30 minutes late, but not more. So how wide is it from 24 to 30? How tall is it between 24 to 30? Okay. 30, which is? 1/5. Alright, so we have a 1 in 5 chance that our friend will be between 24 and 30 minutes late, which is roughly 20%. Yes?
So, on your x-axis, if you had like 25, then your height would be 1 out of 25.
Right. If your whole graph was 25 long, then yes, you would have 1 out of 25 for your height. Other questions? All right, let's take a look at a little bit of a different scenario. So let's say that this friend starts to work on it. They get better at not being late. They're still late, but they're not as late as they used to be. Now they're only between 10 and 15 minutes late. We want to figure out what is the probability that they are greater than 12 minutes late. Now, first thing to notice here is that in the previous situation, we were dealing with someone who was going to be between 0 and 30. Now we're specifically looking at just the area of 10 to 15. And so that means, of course, that our graph is going to look a little bit different because we're not going to be up to 0. We won't want to touch the y-axis because that would indicate that we're 0. Of course, we're going just between 10 and 15, so it's going to be a much smaller width to our graph. So it should look something like that. We don't start on the y-axis because it doesn't start at 0. We just jump over 1 to give ourselves a little space. 10, 11, 12, 13, 14, 15, which of course is our maximum. And so, of course, we also need to complete the graph by determining the height, so that way we can calculate our probability. So, we use our area formula. What is the area of this rectangle? What is the area of this rectangle? 1, because it's always 1. Area is always 1. 1, number 1. What is the width? Of course, we need to figure out the height. So what is the height of this graph? Questions?
Yeah.
Yep.
I was thinking
Alright, so they're actually asking us what is the probability that they are greater than 12 minutes? What's the probability of greater than 12? So of course 12 right here.
Wait, I can't. Wait, so 12 minutes later?
Greater than 12 is what they're asking for.
What 12 minutes?
And yes, it's a very important thing to have a graph and shape what you're looking for. It helps to give you an idea, first of all, of what range you're looking at. It also helps to give you an idea of the space, kind of relate it to a more or less probability. Next time we actually will be doing a lot of coloring, so today just a little bit of coloring. Alright, so what is our width here? 12, 15. So if it's 1, 2, 3, 6. What is our height? Multiply those together, of course. We get 3/5, 0.6, not 60%. Questions? Alright, so we have a little practice here with our uniform distribution. So take a few moments when you get the paper, look at number 1, see if you can set up the graph. Yes. Oh, if we haven't already done so, we pass up the ones that we did not write on earlier.